ChatGPT is making waves worldwide, attracting over 1 million users in record time. The uses for GPT are endless, but not everyone takes the time to understand how these models function. This video will explain the fundamental concept of LLMs, large language models, and the transformer architecture, which is the building block of all language models with transformers in simple terms. GPT is a type of language model that has gained significant attention in recent years due to its ability to perform various natural languages processing tasks, such as text generation, summarization, and question answering. Let's start by understanding what large language models, LLMs, are. Large language models, LLMs, are trained on massive amounts of text data. As a result, they can generate coherent and fluent text. LLMs perform well on various natural languages processing tasks, such as language translation, text summarization, and conversational agents. LLMs perform so well because they are pre-trained on a large corpus of text data and can be fine-tuned for specific tasks. GPT is an example of a large language model. These models are called large because they have billions of parameters that shape their responses. For instance, GPT-3 has 175 billion parameters and was trained on a massive corpus of text data. The basic premise of a language model is its ability to predict the next word or subword, called tokens, based on the text it has observed so far. To better understand this, let's look at an example. The above example shows that the language model predicts one token at a time by assigning probabilities to tokens based on its training. Typically, the token with the highest probability is used as the next part of the input. This process is repeated continuously until a special token is selected. The deep learning architecture that has made this process more human-like is the transformer architecture. So let us now briefly understand the transformer architecture. The transformer architecture is the fundamental building block of all language models with transformers, LLMs. There are 7 important components in transformer architecture. Let's go through each of these components and understand what they do in a simplified manner. Inputs and input embeddings. When a user types in words, these words are converted into numbers so that machine learning models can understand them. This conversion creates input embeddings, which are numerical representations of the words. These embeddings work like a dictionary that helps the model understand the meaning of the words by placing similar words close to each other in a mathematical space. During training, the model learns to create these embeddings so that similar words have similar numbers. Positional encoding. In natural language processing, the order of words in a sentence is important for understanding its meaning. Traditional machine learning models, like neural networks, don't naturally understand word order. To solve this, we use positional encoding, which assigns a set of numbers to each word's position in a sentence. These numbers are fed into the transformer model along with the input embeddings. This helps the GPT model understand the order of words better, allowing it to generate grammatically correct and meaningful sentences. Encoder. The encoder is a part of the neural network that processes input text to understand its meaning and context. In GPT, the encoder first breaks down the input text into tokens, which can be individual words or parts of words. It then uses self-attention layers, which can be thought of as complex computations, to create hidden states that represent the text at various levels of detail. The transformer model uses multiple layers of these encoders to achieve a deep understanding of the text. Outputs, shifted right. During training, the decoder in GPT learns to predict the next word by looking at the previous words. To achieve this, we shift the output sequence one spot to the right so the decoder can only see the words that came before it. GPT is trained on vast amounts of text data, which helps it generate coherent text. These datasets contain billions of words and sentences, providing GPT with extensive language data to learn from. Output embeddings. Models can only understand numbers, not text. So, outputs must be converted to a numerical format called output embeddings, similar to input embeddings. These embeddings also go through positional encoding to help the model understand word order in a sentence. A loss function measures the difference between a model's predictions and the actual target values. It's crucial for complex models like GPT. The loss function adjusts parts of the model to improve accuracy by reducing the difference between predictions and targets, which boosts the model's overall performance. Output embeddings are used during both training and inference in GPT. During training, they help compute the loss function and update model parameters. During inference, they generate output text by mapping the model's predicted probabilities for each token to the corresponding token in the vocabulary. Decoder. The decoder is the part of a model that creates sentences based on the given input. When training, it learns to predict the next word by looking at the words that came before it. In GPT, the decoder uses the input and the context from the encoder to generate natural-sounding text. It has several layers to help make its predictions more accurate,